this is exactly the same stuff we've been doing about redox reactions, finding your strongest, writing the half reaction down, the exact same thing. Only this is an application. Okay? So titration, the basic titrations you would have done in Chem 20 maybe. And so you should know these parts of apparatus, etc. But when you did a titration, you did an acid-base titration. So an acid and a base and an indicator, probably phenolphthalein as your indicator, and you would have let the phenolphthalein change from colorless to pink, and as soon as it changes pink, you stop. And you write down the half reaction, and you do the mole highway, down one column, across, down the other, to find out a concentration of one of them. Okay? This isn't an acid-base titration, this is a redox titration. But the principle is exactly the same. So, but there are some key words that you need to know. So, in a titration, one reagent, the titrant, is slowly added. So the titrant exists in the apparatus called a burette. Okay? Today we'll be doing titration calculations, and tomorrow, if I can find the materials, we'll be doing an actual titration. It's going to be a bit tricky because there's lots of this in the class, so we'll see how it goes. But anyway, so burette is this tall, skinny column, which is in increments from 0, 10, 20, 30, 40. The zeros at the top, because it's about the volume that you have used, the volume that has come out. That's the important part. I'm not measuring how much volume I have in my burette. I don't really care. I care how much came out, so therefore 0 to 10 means 10 mils came out. 10 mils is where my reaction is. That's why it's in reverse for normal things. This is called a stopcock. It's also called a stopcock if it's in your tap at home. You probably just don't know it, that it's called that. Okay? So in your tap at home that you turn on the garden hose with, you know, the water hose, whatever you call it, that inside is called a stopcock. So if it was leaking and you had to go to the hardware store to replace it, that's what you would buy. You don't just go and buy the tappy thing that hangs out at the end of the, yes, okay? So that's what that's called, and it works on the exact same principle. So we'll look at how it works when we get one. And then this is an Erlenmeyer flask that I have down there. My sample is inside, and sometimes you need an indicator, but more often than not, if you've noticed, redox reactions have a color change in themselves. So I don't always need an indicator because the color change indicates that the reaction has happened already. Okay, like the purple potassium permanganate turning colorless, the orange potassium dichromate turning green. Okay. Okay, so in a titration, one reagent, the titrant is slowly added to another, the sample, until the burette, until an abrupt change in the solution property, which is called the endpoint, occurs. Okay? Everybody okay with all of those definitions and what they look like? The other word that you probably don't know then is pipette, which is a tiny instrument, and you'll see a pipette when you do your experiment. Looks like this, and it's a little bit like a straw, I suppose, where it's calibrated to an exact volume. So let's say 10.00 mils if you fill it up to that line there. Okay, so it's exactly the same as a measuring cylinder, only it's far more precise, 2 decimal places precise. So that's why I would use a pipette over a measuring cylinder. Okay, so, and then I put like a turkey baster bulb at the top to suck it up the straw. It's essentially a straw, and then carry it across. Hands up if you've used a pipette before. Fabulous. Hands up if you've used a burette before. Fabulous. So we should be all right for tomorrow. So, once I've figured out what's going in my beaker, I still do the same thing. I list the species present, I find the strongest oxidizing agent, the strongest producing agent, and I write those half reactions. So here, if I'm adding potassium permanganate, it's acidified. It's probably that half reaction that's my strongest oxidizing agent, because by now you've seen this potassium permanganate strong oxidizing agent so often that you should have that drilled in your head. But that's way up on the top left-hand side. Okay, now the bit that I insist that you know, we've dabbled on it, but if you haven't been here, you probably haven't seen it very much, that this is purple in color and this is colorless. And therefore, when I know this is reacted, I know that my solution will change from purple to colorless, as will yours tomorrow. Okay? When all the sample's been reacted, 1 extra drop of potassium permanganate will change. Actually, this is going to change from colorless to purple. Well, this one does, as it's written. Depends on what you have down here, and depends on what you have up here, as to whether you are dropping in purple or it is purple at the moment. Okay? The endpoint is called the equivalence point. So here's another highlighted word for you. I've seen both as in the diploma exam for you to define. Okay? And when we get into the acid-base unit, we talk about these in more detail. So the equivalence point and the endpoint are, for now, the same thing. It's called the equivalence point not because they equal each other, but because their mole ratio equals each other. So when I finished writing the balanced chemical equation, the big numbers are all balanced. I have enough of 5 moles of this and 2 moles of that, for example. Make sense? Not because they are equal, but because their moles equal. Or actually, in redox reactions, because the electrons have equaled. The amount given off and the amount taken in are the same. Okay? But the equivalence point is more about the stoichiometry balanced big numbers. Okay, dichromate ion is also commonly used, and I've written down the orange to green for you. That's used in breathalyzers. So roadside breathalyzers that the police officer will give you, or you can buy breathalyzers for your glove compartment. I strongly suggest you do that. In France, it's mandatory. Every car must have a breathalyzer in it. How cool is that? So, a personal little breathalyzer, you're not sure, 1 drink, 2 drinks, was that too much, was that not too much? Because it totally depends how tired you are, what you've eaten that day, right? So therefore, you just take your own little test. And then that'll help you decide. So, roadside kits, they turn from orange to green because this is a half reaction that's happening inside. And if this is gaining electrons, then the losing electrons is the ethanol. So the ethanol will lose electrons, and this will gain electrons, dichromate, and you'll see the dichromate change from orange to green. Whereas carbon dioxide doesn't lose its electrons. It would not be a spontaneous reaction, and therefore you wouldn't see a color change. Okay? So it's the ethanol that's on your graph. In order to perform stoichiometry, the results of the titration of the concentration of the titrant must be known. So you need, just like the other stoichiometry that you do in Chem 20, you will know 3 things and not know 1. Okay? You'll know 2 volumes, 1 concentration, and try and find the other concentration. Normally is how it goes. If the titrant is not a standard solution, do you know what standard solution means? There's another key word for you. What's standard solution mean?
STP or whatever.
Oh no, but good thought. You're right. It could be standard temperature and pressure. In fact, that's actually part of it sometimes. But in this case, in titration, if I have a standardized solution, it means I know its concentration. Known concentration. Okay? So it's not at standard conditions, but it has been standardized. I know its concentration. Okay? There. So if it's not a known concentration, you must find its concentration first before you can do your reaction, is what that last paragraph is saying. Okay, questions on that packaging note or that page notes? Okay, so I want to go here. I want to go to this one now. Find this sheet in your package. Okay, so here's an example. This is exactly like Chem 20. The only difference is that in Chem 20, I will have given you the reaction. A plus B yields C plus D. Here, you have to create the reaction. Because it's a redox titration, You create it the same way you've created these other redox. Not single replacement, not double replacement, not those science 10 ways, but rather list your species, find your strongest, right? That's what we're going to do here. So, what is the concentration of chromium 2 ions in a solution obtained from a stainless steel fork? One of the hardest things that students find about this is finding out their species. Okay? So I really want you to pay attention as to how I make my species list here. And after that, students seem to be okay on their own. But because it's not, you know, like the paragraphs are hard, and because this paragraph is a bit even chopped and changed everywhere, they find it really difficult to figure out what's reacting. So concentrate on that part. I'm just going to lift this up slightly. Okay, so there we go. So I have this concentration. Everybody recognizes that's a concentration right away because it says moles per liter. Of potassium permanganate. What's present so far? K plus and MnO4 minus is titrated to oxidize. This is a volume of what though? This is a volume of chromium 2 plus. Everybody okay with that? 25 mils of chromium 2 plus. And then what does this mean? This is going to throw people off to chromium 3 plus. What does that tell you about the half reaction that's happening right there? I'm going from Cr2 plus to Cr3 plus. Do I need to look that up in my data booklet, or can I just do that quickly on my own? I should be able to do that quickly on my own. Which side does that one electron go on? The right. Oh, bet you that threw some people off. Why? What's the quick way of knowing that? I think the math, yeah, is going, if I have 3 plus on this side and 2 plus on this side, I better have a 1 negative, so that positive 3 and negative 1 make positive 2, and this side is positive 2. For me, that's the fastest way. Chemically though, you say, to go from 2 plus to 3 plus, I must have given out 1 electron, and so I've produced 1 electron. That's what you say chemically. Okay, everybody okay with that? Now if you want, you can find this in your data booklet. It'll be in there. Chromium 2 plus going to chromium 3 plus. Just make sure you go the right way in your data booklet. But it's in there. Okay, so I need to rub some of this stuff out. This stuff and this stuff. Okay. So that's one half reaction. Oh, and then I keep reading and it says to 3 plus ions. And then it says an acidic solution, which is good because what do I know about the potassium, what is it? Potassium permanganate, it has to be acidified, right? Okay, and an acidic solution, so K plus, or H plus. So, I could list all my species. K plus, MnO4 minus, H plus, water, Cr2 plus, and I'm going to get a little thrown off about the Cr3 plus, but I know it's 2, so it's produced, so it doesn't go in my list. Because I'm making it, not starting with it. So if I wanted to list all my entities, I could. K plus, MnO4 minus, H plus, H2O, Cr2 plus. And I could find, start on the top left of the data booklet, start working your way down, find the strongest oxidizing agent, write that down. Start on the bottom right, find the strongest reducing agent, write that one down. But this tells you already. So if you've been practicing in your book, if you've been here every time, this should be much faster for you. You should be able to just write this down and then also look for the MnO4 minus one. plus how many hydrogens? 8. 8 pluses plus 5 electrons goes to Mn2 plus 4 waters. Okay? So, if you're not ready to just pop that out of this, who's ready for that? Who could already see that reading these, I would have had those 2 half reactions? Okay, I should have a few more hands than that. And over here, who would be able to write those species? And then from that species, go to the top left-hand corner, work your way down, and have found that these 2 are your strongest oxidizing agent, that would be your strongest reducing agent. Okay? So if you're comfortable with that, I need you to jump to this step now. To just being able to read and write your half reactions. Why? Simply because it's faster. And on the diploma, you have 1.7 minutes to answer this question. Right? So the faster you can do it, the more you save yourself some time for the harder, longer questions. But if you're not ready yet, still go back up here. Nothing wrong with that. But the next step is to do that a little bit quicker. Okay, so then you write the net reaction, right? So I'm just going to, I'm running out of space here. Right, so I'd have, oh, I forgot to balance it. So I'd have 5 Cr2 pluses and an NNO4 minus and 8 H pluses, and they would make 5 Cr3 pluses and an Mn2 plus and 4 H2O. What would the diagnostic test be that I had reached the endpoint? Color change from? Everybody? Yes? Be familiar and be comfortable with that word diagnostic test. Just means what would you see in a lab. Okay? Okay, and then now I put the information, now it looks like Chem 20. Okay, so that was the Chem 30 bit. Now this next bit is the Chem 20 bit. What information have I been given on my sheet? I actually don't know because I can't see up there. The concentration is of the potassium permanganate, yes? So that goes under, now this is also a bit confusing, there's no potassium permanganate here. Which ion is part of the potassium permanganate? This one. Do you see that? So I have to read the potassium permanganate to be the MnO4 minus. So the concentration is 0.0114 moles per liter. Is titrated to oxidize, that's the volume of the chromium 2 plus. And then in my evidence box, it's titled Volumes of Potassium Permanganate Solution Required. So these are volumes of the potassium permanganate, because that's what the title says. So the volume of that goes there. And how do I calculate these volumes? I subtract them. I do an average of them all. Pardon?
The 3 closest.
You have to have 3 that are within 0.2. So there'll be 1 that you can discard normally. Normally there's 1 you need to discard because it's like an outlier or an anomaly. Okay? The average is too far out. So if I do the subtraction on all of them, the subtraction of those ends up being, somebody help me, who's doing it on the calculator right now? 11.5. This one? 11.2, this one.
11.1.
Okay, so do you see how that 11.5 is an outlier? So we exclude that. See that? Because that's the first one they did. So what you say is they overshot it. They put too much in. Oh, there was the color change. Whoops, I just passed it. Oh, I put too much in. I've overshot the endpoint. Did that ever happen to you when you did it in Chem 20? You end up with that really deep pink if you're using phenolphthalein indicator, right? And your teacher goes, no, that's too dark of a pink. You're looking for something a lot paler. Okay, so that's what happened to them there. They overshot the endpoint. So what we need to use, though, are 11.2, 11.1, 11.1, added up, divided by 3, because I'm only using the 3 results. And that volume then goes here, so that ends up being 11.13, rounded to the significant figures, just 11.13 mils. Okay, and then what do you do for stoichiometry? Right, you find the number of moles of your known, so that's this one, concentration times volume, which equals 0.0114 times 11.13 mils. I've left it in mils, so my answer is going to be however many millimoles.
0.1269.
Okay. I leave that value in my calculator. Everybody okay with millimoles? Who does not like the fact that I've used millimoles? Okay, deal with it. All right, and now what do I do? Now that I've gone down that stream, right, I want to cross the bridge into the next stream. So to cross the bridge, I look at my mole ratio, which is a 5:1. So it's a 5:1 ratio, so I'm going to have to multiply by 5 to convert that to the number of moles on this side. So 0.1269 and all the decimals in my calculator times 5 gives me, Evan's being a good calculator guy today.
6.6344.
6.63.
Sorry, 0.63.
Oh, 0.6344
44.
Still the millimoles. That's not very neat. I'll rewrite that. And I'm asked to find the concentration of this. I didn't even write that down. Concentration equals N divided by V, so I have 0.6344 millimoles divided by the volume is 25.0 milliliters, and oh, conveniently, my millis cancel out.
Awesome.
Which is why I was okay with keeping it in there, because it saved me from dividing it by 1,000, dividing that by 1,000. Okay? And once you've divided those two numbers together, you get
0.0253
moles per liter. Moles per liter, pardon me. Concentration.
Why do you use the moles of MnO4 as a say, like how can you just multiply that by 5 and assume that it's the same first?
Because when they react at a 5:1 ratio. So once I've gone down this column, I can go across the bridge by using the mole ratio,
Okay.
and then I go down again. So if they react 5 moles for every 1 mole, but I don't have 1 mole, I have 0.1 moles, I should have 0.5 moles reacting. Nearly. Right? 5:1 ratio should be 0.1 to 0.5 ratio. And that's what you're doing. So you gotta convert it by multiplying by 5. Everybody okay? Right, so not only is this reinforcing your listing species, finding the strongest oxidizing agent, it's also combining that with your Chem 20 stoichiometry and putting the two things together. Okay? So we're going to practice some of this. We also have a quiz tomorrow. Does anybody have any questions?